It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least, so far, nobody has found a truly conclusive way. In this presentation it will be shown that the job was in principle already done by no other than the German mathematician David Hilbert, and there is no need to combine quantum theory and general theory of relativity because the latter already contains the first. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this presentation, we will concentrate on the quantum gravity derivation of so-called cosmological metric solutions. Shown here, to give an example, is the holy grail of cosmology, which is the Friedmann-Lemaitre-Robertson-Walker metric. It describes universes of constant Ricci curvature R, thereby using the cosmological principle, saying that, on bigger scales, our universe is homogeneous. We have the situation of spherical, hyperspherical, and no curvature, which is to say, the completely flat space-time. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation we will now show what Hilbert had missed, or taking Hilbert's genius, simply not considered important enough to be mentioned at all. In connection with the Friedmann-Lemaitre-Robertson-Walker metric, Hilbert's formula does not work without a meta term, which is to say, without Lm. This on first sight seems to make a lot of sense, because obviously the universe contains something, and this we realize as matter. However, in our previous presentation, especially see part 1 of this video series, we have shown that we do not need the meta term Lm to obtain matter. And so we had always set both lambda and Lm equal to 0 and just proceeded with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. In here, however, for completeness, we will keep the cosmological constant and only set the meta term equal to 0. We will see in due course that this still gives us reasonable and, what is more, matter-containing universes. Now, by following Hilbert's classical derivation, we obtain the so-called de Sitter vacuum Einstein field equations. Obviously, these equations do not contain any matter. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel, which becomes even more impressive when writing some of our abbreviations out. At the moment, this does not help us much, but when introducing a metric tensor which mirrors the typical structure of the Friedmann-Lemaitre-Robertson-Walker metric in a rather general manner, we obtain something very interesting. The experienced listener will already make out the typical terms known from the famous Friedmann equations, only that this time we find a funny parameter dependency and, as we should remind at this point, have not even considered any postulated matter so far. In order to work out the new dependencies, we have to further evaluate the kernel of the integral. At first, we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. As a result, we obtain two equations, a scalar and a tensor one. For the time being, we ignore the tensor equation for example by simply assuming that the variation of the metric tensor gives 0. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us the following partial differential equation, and by inserting our new setting for the metric time component g00, we separate the time derivatives. In case where neither the metric determinant g nor the metric time component g00 depend on time, the latter equation can be simplified. Now, just as within the classical Friedmann approach, we assume the scaling function to solely depend on time. Leaving it to the interested listener to solve the general case, we here only consider the situation with vanishing Ricci curvature and lambda being 0. We find that for a certain setting of our parameter tau, which distinguishes the metric timescale from the spatial one, we obtain an exponentially expanding spatial part of the universe. But not only the spatial part would exponentially expand. Also, the effective speed of light would increase due to our special solution to the scalar part of the quantum Einstein field equations. This we see when observing the metric time component G00. Here we have only considered the example in 4 dimensions, where with the condition of tau equals 2, we end up with such an inflationary scenario. Could this explain the inflation period of our early universe, as it was suggested by Alan Harvey Guth? Could it be that the universe literally and spatially exploded the moment its dimension reached the value n equals 4? Could it be that in the period of inflation also the effective speed of light grew to a huge number, so that a much faster way of communication existed for a brief moment in the history of our universe? If so, what had stopped the process after that? Well, many things could have happened, especially as so far we only considered a flat space with both lambda and r being assumed to be 0. The simplest possible explanation is a change of dimension or the parameter tau. The moment, namely, the special ratio of tau to n breaks down, the scaling function F has to take on the following form. We realize that there are a variety of constellations where the exponential growth could have stopped and could have taken on, for example, a linear growth instead. For completeness, we give the corresponding metric tensor for 2 of such cases, namely n equals 4 and tau equals -1, and n equals 6 and tau equals 0. Having seen that a lot depends on the actual choice of the conditions for the scaling function F, we realize that there is a great variety of options. A simple change of sign in our previous conditions, for instance, changes our logarithmic wave function to a square one. Therefore, we here present a generalized form for the F condition with an arbitrary function h of f. In due course of this series, we will see how this helps us to perhaps better understand, among other things, stuff like the origin of the Higgs field, the Young-Mills mass gap, and the 3-generation problem. Just as an example, using the first line condition for F, and once again assuming the f to be solely dependent on time, we obtain 4 solutions for our wave function f in the case of non-vanishing Ricci curvature. In the case of negative curvature, these solutions give peculiar oscillations, which are due to the square occurrence of f in F, summing up to a simple periodic scaling behavior of the metric tensor. We cannot overlook the fact that the behavior of these solutions is similar to the particles at rest. For this, we refer to part 5 of this video series. For positive curvature, we obtain exponentially growing universes with a funny behavior near the Big Bang, where we find a non-zero scale at t equals 0, followed by a decreasing scale and a non-zero minimum after a certain time t equals t0. With a scenario like this, our universe would never have been squeezed to a point, but always would have had a certain size. Even at its minimum, the universe would not be a mathematical point, but an entity of a distinct size. As it will be shown later in this series, this minimum size is connected with the Higgs, or at least Higgs-like, field. This automatically brings us to the suggestion that perhaps the total curvature in fact does vanish, but that there is a negative r which leads to oscillating solutions, and thus particles, and a positive r of equal size that gives the exponentially growing universe. Here we would have a rather constructive zero, or r minus r, namely 1, which would have made our whole universe, which is to say its matter and its expansion. In fact, so it could be assumed with the information at hand and the obvious observation that our universe appears flat on bigger scales, without the expansion we would not even have any matter at all. But there are more possibilities, even some which do not require a Ricci curvature at all, not even an effectively vanishing one. When going back to our extended, which is to say scale-factored Hilbert variation integral, and bringing the tensor and the scaling part back together, we suddenly see that even in a completely flat spacetime, meaning where all r terms are vanishing, we can still have a scalar equivalent for our Ricci r in order to, hopefully, obtain the necessary particle and or scaling expansion conditions. We only need to remind ourselves that the tensor part under the integral has to be summed up with a contravariant variated metric tensor, and this just gives a scalar again, and we are comfortably back with the right equation for the metric creation of particles and or exponential growth. For completeness only, we here also give the unabridged form of this equation in the case of tau equals 0. By inserting what we know about our scaling function capital F, we end up with an equation completely depending on the inner wave function f, its variation, and the variation of the contravariant metric tensor. There too could be an intelligent or constructive zero assumption when just playing with the variational terms, which is to say that the delta terms appear positive and negative and effectively sum up to 0. But this they don't do without before being used as substrates for both matter and exponentially scaling growth. It should be pointed out, however, that there are also other options to metrically derive matter and potentials via additional dimensions. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out that we do not consider us the first to have found the connection. In principle, namely, it was all already inside Hilbert's ingenious approach, and he only could not see it because at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. The next smaller step is just the naturalized AI, which still is a small Manhattan project. This, too, already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are just smaller service projects.